right, so we learned about what to do if you're self-born, right? We learned about the prisoner's dilemma, which is like both of those prisoners are going to snitch on each other. They're going to confess to the crime rather than keeping their mouth shut. And we noticed that seems paradoxical, but game theory told us why it would happen. So let's continue with the idea of games, where games are in quotes. All right, so here's a fun one: cake cutting. All right, so this is an interesting game. Maybe you've played it with like a sibling or something before. It's like you have a piece of candy or something. It's like you cut it, like you cut the cake, and then your sibling gets to choose which piece they want, right? Something like that. So that is a game that we can consider right now. And I'm not sure if this is cooperative or non-cooperative, because remember that cooperative game theory, and the internet is kind of confused too. I tried to look it up. Cooperative game theory. That's when, like, bless you, if you have an alliance, like you want to like make pacts with people, then it's a good thing. Apparently, if you're playing this game where like you cut the cake, your sister chooses which piece to take, you're kind of forced to cooperate. So you're driven into a wall. So maybe it's either cooperative or non-cooperative. We're not sure. So yeah, the game is, surely you've played this, or at least you've heard of it. It's like one of you splits the candy bar in half, and then the other person gets to pick which half they want, right? And so what is the optimal strategy for this game? Assuming you want a piece of that cake, you want as much cake as possible, right? What should you do? How should you cut that cake? You have several options, right? How should you split the candy bar in half? Well, if you want the most cake, you better cut it in half, right? You better cut it in half, because then there is no difference between the two pieces, and no matter which side your sibling picks, you're still getting a good piece, right? So if you cut the cake just like this, perfectly in half, the best drawing of a 3D cake, then no matter which side your sibling picks, you still get half a cake. Yeah. If you were greedy and say you cut the cake like this, then you know that your sibling's going to pick this part, right? And so you're out of a lot of cake at that point. So you're going to get the smaller half because they're going to pick the bigger half. So I think that would be the optimal strategy if you want the most candy or cake. Okay, so have we heard of this game before? Have we played it with a sibling? So yeah, that's a thing. And you can think of that as a game. That is a good segue into the idea of a new kind of, what's it called? A new kind of like equilibrium. We learned about Nash equilibrium. This is a new term that kind of has to do with that. It's called Pareto optimality. All right. So it's again named after somebody. It's a fun idea. But let me say these words, and then we'll say what they really mean. Right. So this is like the textbook definition of Pareto optimality. So it's like a resource allocation is Pareto optimal. So we're doling out things to people. It's like we're giving them money, we're giving them cake, something like that. We're allocating resources. We say that it's Pareto optimal when if you were to change that allocation, if you were to cut the cake in a different way, then that always leaves somebody else worse off. All right, so those are the words, but I think it's going to take some examples to make sense, right? So I would say this is a very utilitarian concept, right? You want to have everybody never worse off than they were before, so very utilitarian concept here. So a resource allocation? It's Pareto optimal. If you were to change the way you did something, you were to change the way that you cut the cake, somebody else would be worse off. Let's see. Which ways are best and Pareto optimal for cake cutting? So like you'd ask the question then, all right, in the cake cutting game, what kinds of ways to cut the cake would leave somebody else worse off if there was a difference? Like if I nudged the cut over a little bit, would somebody be worse off? So let's see. Your optimal allocation, right? At least if you want cake, the cutting it in half, that is Pareto optimal, isn't it? If you think about it, like here's you cutting the cake in half again, 3-dimensionally. Do you see that? If you were to change the way you cut this cake, right? You cut it like this instead. Boop. Just a little bit more on this edge. And it's like that now. Do you see how somebody's going to be worse off? You're the one who's going to be worse off now because your sibling's going to pick this bigger piece, right? So somebody's worse off the way if you were to change the way you cut this cake, had you cut it in half, right? Does that make sense? So this is cutting it in half is a Pareto optimal allocation, all right? So that's a good idea. It makes sense, right? Somebody's worse off if you change the way you did it. But it also, again, like a paradox maybe, it just so happens that any way that you were to cut the cake is going to leave somebody worse off. So it's like no matter how you cut the cake, it's Pareto optimal. Look, if you cut the cake in the weird way, if you cut it in the greedy way, so you cut it like this. If you were to change the way you cut this cake, still, right, somebody would be worse off. It's just now it's going to be your sibling. Like say you cut it over here instead. Do you see how now your sibling's still going to pick the bigger piece, but they're getting a smaller, bigger piece? So it's still Pareto optimal. It's just like you're the one who's benefiting this time instead of your sister, your sibling, whatever. Okay, so that's interesting. All right, so that's Pareto optimal. That's another term. All right, I hope that makes sense. And this actually gives us another reason to say why that prisoner's dilemma, this idea here of like, why are they going to both confess? It also tells us why that is, like, it seems so weird in our minds, because the Nash equilibrium that we found for the prisoner's dilemma, that is not a Pareto optimal outcome, all right? Because there is a way to change the allocation. Like they're gonna focus on this. There's a way to change the allocations where they're better off, isn't there? That gives us some words to say to describe the way we feel there and why it doesn't make sense. So yeah, Pareto optimality is a good idea, and it helps you explain things. So yeah, sometimes a resource allocation, we want them to be Pareto optimal. All right, so I guess technically, time spent in jail time is a resource. Cool. All right, so if we're good with that, any questions about that example? Some new terms. I would like to teach you one more big term, I guess. That's a big deal in game theory. I want to teach you how to share like an Uber ride or a Lyft ride with somebody. I don't know if the app probably does it for you, but look, here's the setup, right? We're going to discover a number together. It's going to be great. So if you were to share an Uber with somebody, first of all, that is a cooperative game, right? You guys are not going separately. You're going to share the fee, and so you're both going to save some money in theory, right? So here we got two people, person A and person B in computer science. Instead of person A and person B, we always say Alice and Bob. So Alice and Bob, they're sharing a taxi. They're trying to go home from dinner or something. And Alice lives on the way to Bob's house. That's key, right? So what happens would be this, right? So here is my best drawing of a car. Boop. Of a taxi. Boop. There's the taxi. And here is like the path home for both of them. So like here's Alice's house on the way home to Bob's house. So they're both going to share the same ride because they live on the way to each other's house. And so they'll just like let Alice out halfway home. Okay, so that's how that would work. And let's say that here are the fares for tonight. If Alice were to take a taxi just by herself, she lives very close, she would pay $5, all right? And then if Bob got a taxi by himself, he'd pay $12, all right? Let's say that that's the amount that the app is telling you. And then they're both going to take the taxi together. And so because Alice can just like get out at a stoplight or something, it's not going to take any longer. The fare for both of them to share the ride is going to be still $12, the price to take Bob home, right? So the question now is, how much should they split the bill? Who should pay what? All right, and we're going to come up with a fair allocation here. Okay, so how much should they pay? If the total cost is $12, do you see how it's not good to split the bill perfectly? So like that would be $6 and $6, right? That's a horrible deal for Alice, right? Because she could have just gotten a taxi by herself, and she would save $1 there. So that's not fair. Fair for Bob, I guess. Bob gets a good deal, but that's not how it should be, right? So Alice should be paying less than $5 somehow, all right? That's the goal. And then Bob should hopefully also pay less than $12. So it would add up to $12 total, though. Okay? So that's what we want. And here is how we fairly split the bill. This is a good number. It's like we're discovering how to properly cooperate in the most efficient way. So what we want to do to calculate the best fare, the one that they should pay, is, again, we're going to take like an average, kind of like how we did with the prisoner's dilemma. That's going to be important again. So we're going to compute what's called a shapely value. All these things in game theory named after other people. So silly. That will give us what we need here, all right? So here's how you compute the shapely value that will give us the fair taxi ride payment allocation. All right. What you do is you think about all the different ways that Alice and Bob could have paid the taxi driver. It's like who pays the taxi driver first, and they're all going to pay like their share, and like the person who pays second would pay whatever is left over of the total bill. All right, that doesn't make a lot of sense. Let me show you what I mean by that. It's like consider the permutations of who pays the remaining bill in what order. What I mean by that is like, all right, either Alice pays the bill first, and then Bob pays the rest, or Bob pays his bill first, and Alice pays the rest. And we're thinking about the bill in terms of their original values if they were to take the taxi separately. All right, that's what I'm saying. So if Alice takes the taxi first, or like if it's her if it is her turn to pay her share first, she would pay $5 total, right? And then Bob would pay the rest. So in this universe, if Alice paid first, like she pays as much as she needs to, like her final bill, and then Bob pays whatever's left of the total ride. So that's 12. So that's $7 to add up to 12. So Bob would pay $7 in that universe, right? This doesn't make sense why this will work, but it will work. And then, all right, let's consider this order. If Bob pays his fair share first, he'd pay the $12, right? And then Alice would pay whatever's left over, and that would be $0 if she gets to go to second, right? So it's a weird idea. It's like, consider those kind of orderings of like, somebody's going to pay their full bill first, and then the next person pays the rest of the total. And now we're kind of like, we got two universes here. And what we do is we take the average. We take the average for somebody. It's going to be symmetric, so it doesn't really matter. But let's do it for Alice, all right? If we take the average payment for Alice in these two universes, that will give us a good cost, right? So Alice, what's Alice's cost in each of these? Alice's cost for the ride. In the first one, Bob is stingy. She pays $5, her total bill. But in the second one, Bob is nice, and she pays $0. So the average of that is $2.50. And that is apparently the most fair way to split the bill. So Alice will pay $2.50, and then Bob would pay whatever's left, which is what? $9.50? Something like that. So that is apparently the fairest way to split this bill. And so Alice is paying less, right? It's not 6 and 6. She's still paying less than her original bill. And then Bob is still also paying less than his original bill, the $12. Does that make sense? So that's one way to do it. And I don't know, like, have you guys shared rides in apps before? Like, can you like say like, we're going to split the bill or something? Maybe they're calculating this. I don't know. Usually it's just somebody pays the whole thing and then somebody else like Venmos you later. But like maybe when you make your own ride sharing app, you'll calculate this for your users if they're having multiple steps. All right. So yeah, that's a fun example. Any questions about that? So you can use that when you have to split bills now. So okay. The last thing I want to show you about, it's going to take 3 slides to get through. The last thing I want to show you about game theory is let's actually talk about a game for once. Let's talk about tic-tac-toe. It's a simple game, and I'd like to teach you how to solve tic-tac-toe. It is, I mean, it's a game that you could always win or at least tie if you get to go first, right? I'm going to show you how to discover the right strategy for tic-tac-toe. And you could apply this to other games like chess or checkers or something if you had enough computational power. But tic-tac-toe is nice and small, all right? I want to teach you an algorithm. It's called the Minimax algorithm, all right? It's a way to search for an answer in a game, and it will help you find the optimal strategy. It will tell us, like, if we are, like, X or something, if it's our move right now, it will tell us exactly where to go. All right, I know it's an easy answer right here to win the game, but imagine you didn't know that. So what we do is we kind of play out the rest of the game, and we decide we're going to simulate what's going to happen, like no matter what might go on. So like we're going to pretend like, okay, maybe X goes here, okay, maybe X goes here, okay, maybe X goes here, and then it's O's turn. And we're going to like see all the ways that O could make a move. So that's what we're going to do. All right. So we're going to simulate the rest of the game, and that's going to tell us the best move to play. Let's pretend in tic-tac-toe X always goes first, so it's X's turn right now. And what we do in Minimax, in this algorithm, is it's either our turn or our opponent's turn as we're doing our simulation, right? So like let's say it's our turn right now. We care about winning. So when it's our turn, we're going to try to make the move. We want to make the move that maximizes our chance of winning, right? That makes sense. We want to win. And then when it's our opponent's turn, like we're simulating their move too, like we're going to try all the possibilities, and it's their move after us. And just like keep When it's their turn, we're going to assume that they're good at the game, and they're going to want to make the move that minimizes our chance of winning. Does that make sense? So we're going to maximize the outcome when it's our turn, and we're going to pretend that our opponent wants to minimize our chance of winning when it's their turn. So that's why it's called mini-max. It's like it's going to keep flip-flopping. When it's our turn, we maximize. When it's their turn, we minimize, because they're going to try to get us to lose. If there's a move they can like force us into, they're gonna take that move, right? Assume your opponent is good at the game and always will make the best move. All right. So yeah, we're just going to simulate all the different ways that we could play this game. So like there's like 3 moves for X, and so like there's 3 new potential game boards that we could have after that. And then sometimes you win the game in that move, but other times there's still more moves to be played, right? The game's not over yet, so we're going to simulate O's move after that, right? Then there's always like there's 2 moves for O left, right? We're going to draw the new boards until we hit the end of the game for somebody. Like the board is filled in or somebody has won, right? Or it's a tie, right? So that's the setup. And then I'm going to show you how to compute numbers based on these game boards, these situations, these simulations, and I'll show you what it means to maximize those numbers and minimize them, okay? So I guess my question for you is, here, I'll give you a minute to try it, but like copy down this game board, and you guys can help each other. Pretend it's X's turn, and try to simulate the rest of the game. Try to draw what's going to happen. There's 3 different places that X could go right now, right? So let me try to show you how to do this. So like let's say X goes right here. That's one move that they can make. So the game board, the next state potentially could be that one. Does that make sense? And like you do the other 2 for X. Sometimes there's more. And then the game's still not over. So now it's O's turn, right? And O could either go here or here. And so you're going to draw both of those for O. And like that's going to be all the different ways that that particular game can play out. Does that make sense? Like right now, for this round, it's X's turn. And then under here, if there's still more moves and somebody hasn't won yet, then it's O's turn. It keeps flipping and flopping until the game is over. Does that make sense? So try to fill that in, and then I'll show you, like I'll do it too after a few minutes. And I will show you how to maximize our chances of winning if we're X, and minimize and like pretend that O is minimizing our chances as well. All right? So yeah, see if you can do that. I'll give you a few minutes, and then I'll do it. I'll give you a few head starts, a few minutes of a head start. Convince your neighbor that you're correct. There's 3 slots for X to fill in right now. And then once you've made a move, then it's O's turn. Then there'll be 2 slots for O to fill in. And then potentially, if it's like a tie, there's going to be one. The final move for X is forced, right? I'll give you another minute head start, then I'll fill it in. Questions that came up as we were trying those? Did it make enough sense? Like, all right, the only ways X could do it. That's O's turn. That's X's turn again. So we're going to keep flip-flopping because that's how the game works. Well, let's see. Let's see what needs to happen here. So, okay, the first state was this. I'll try to be small so there's room. Maybe that's too small. All right, so we got X. Here's XOO. OXX, that was the first one, right? That was our starting position. And then there are 3 places that X could go. There, right? If it's their turn. So let's have all of those options as spread out as possible. Just like that. All right, let's see. To save myself time, let's see if I can easily copy this board. So I want it in 3 separate places, right? There, there, and there. We love technology. All right, so X could either go. X could either go here, here, or here. Yeah, I think that was right. So those are all the 3 options. So the game could have gone either of these ways, all 3 of those ways potentially. And then it's O's turn if the game's still on, right? The game is not won yet, so now it's O's turn. O has 2 choices for this one, right? So there are 2 options here. We've got. I guess it's probably faster to just draw it. X, O, O, X, O, X, 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 O, O, X, O, X, X. Cannot undo this move anymore. So O could either go, let's see, here, right there, or they could go right here and win the game, right? Does that make sense? So you do that, and then, all right, this game is still not over, is it? So X has one last move. It's forced upon them. X, O, O, X, O, O, X, X is forced to go right there, and X wins in a few different ways, yeah. Here, this game is over because O won, right? So we don't have to continue. This game, X immediately won, so we don't have to continue. And then this is the last state, right? So, okay, now it's O's turn again. O has 2 options, one of those 2 slots. So let's see. What are their options here? They could go either X, O, O, X, X, X. They could either go, let's see, here, just like that, or here, yeah? So this way they won the game, don't have to continue, but this one, still no one has won the game, right? So there's one last move to be made, one last state of the game to go to, and that would be where X wins. O, O, X, 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 just like that. All right, does that make sense what I just did? Is that what we did? All right, so here's how you do minimax on this. All right, we're going to compute numbers. It's going to be from the bottom up. We're going to compute numbers based on, like, it's either our turn or the opponent's turn. And it's either we won or they won or it's a tie, kind of. If it's a tie, we'll look like, we're going to score our game states. All right, we're going to give them a score. So let's see, what are all the places that we won? But somebody won. So like here, X won. Here, O won. Here, X won. Here, X won. Here, O won. So apparently, for this game state, it's impossible to tie. It's interesting to think about in itself. But we're going to score these game boards. So we're going to give them little scores. So, all right, we're X. We're trying to win, right? So we're going to have a positive number if we win in the game board. So if we won here, like this example here down here, we're going to score that as +1, right? Because we want to win. We want big numbers. If O wins, we're going to score that game board as a negative number. All right, we're going to say -1 means O1. All right, and so this one will be scored out. We're going to start in the bottom. So this one would be scored as +1. This would be scored as +1. And then this one would be scored as -1. All right, does that make sense? That's what we're going to do. And then we're going to work our way up and try to score the things above, right? The ones immediately above. Like we gave this a score, now we give this a score. All right, so when you go up, so this was X's turn. And we were trying to do stuff. This is now O's turn, all right? So what O is going to want to do, oh, I'm so sorry. This is X's turn. Sorry, excuse me. It's about to be X's turn. This is X's turn. They're about to make a move. So when it is X's turn, excuse me, they want to make the move that's going to maximize their chance of winning. So if there are multiple options, we're going to pick the biggest option, Does that kind of make sense? That's going to force our hand, like that's the one we want to take. So that means we would end up choosing this one, and the score for this game state then would be +1. You see that? That's how we do it. It's like it's our turn. We want to maximize our chances over all of our options. We only really have one option, but it's going to be +1. All right, that looks like a weird one. So there. So that's how you score that game board. And now we're up here. Now this is about to be O's turn. All right, and this is why it's called minimax. Now we're going to minimize because when O goes, we're going to pretend that they're a good player, and what they're going to do is try to minimize our chances of winning. So if they have two options, they're going to pick the smaller scoring option because they want us to lose. You see it? So it's going to flip like that every round. So which one is O going to take? Which move is O going to make if they're a good player? They are for sure going to take this move, yes? So that means this game state right here, like the way it's going to play out is negative for us, not good. Does that make sense? Because O is going to for sure do this one if they're smart. Does that make sense? That's what's going to happen. And then same for these. Okay, it's X's turn. We're going to maximize over what we're doing here, +1. So this is going to be +1. But here it's O's turn. They're going to minimize over their option. So they're going to pick this move where they win for sure. And so this game state is going to be -1s, as if this stuff never happened because O is a good player, right? They're going to choose this round, this route. Okay? And then finally we're at this state where again it's X's turn. And so X has a few options. They have these 3 options. And we want to maximize again. It's back to maximization. It's back to we're trying to win. So how do you maximize our chance of winning over these options? We got -1, +1, and -1. We're going to pick the +1. Yeah. That's how you solve tic-tac-toe. You do this for any game state. Just like play it till the bottom. And this will tell you the move that you can make right now. The one that's going to maximize your chances of winning. There might be multiple options, but here's a good one. So the way that this algorithm works out now that we've done this is it's like, all right, if it's time to make this move right now and we're X, we are for sure going to do this. This is what we want, all right? Because that will maximize our chances of winning. Every other option, we do have a way to win, you see? If we made the other move, we do have a way to win, but that's only if O fumbles it, right? We should not bank on that. All right, so I think that is what I wanted to say. So that's a cute little algorithm. Finally, an example of an actual game. And I would say that this is technically game theory, right? So this is something you might program one day if you take like an artificial intelligence kind of class. This is one of those kinds of algorithms. All right. Yeah, so that's kind of fun and a good thing to end game theory on. Are there any questions about that? All right. So yeah, the last new topic I want to give you is called recursion. We won't get to the beautiful stuff, but you wrote an essay about it anyway, so I'm happy enough with that. So what I want to talk about for the rest of the time today is a topic called recursion. It is very interesting, all right? It is a little weird, all right? It's a way to write programs. It's a way of solving problems in programming, and it is a little weird looking. So it's when you find, like you're solving a problem, and you try to find that problem within itself. Seems a little philosophical and vague, right? So you're trying to solve a problem in terms of itself. And you might think, it would make sense, like, all right, is that not just circular? You're trying to solve a problem in terms of itself. Like, will you ever get anywhere if you do it that way? The answer is yes. And the secret is we want to find a smaller version of our problem inside of our bigger version of our problem. We want to unwrap it, kind of like these Russian stacking dolls. So that's a good example. Like you got a bunch of memes about recursion because everybody commiserates together. So like this is like the biggest version of your problem that you're trying to solve. There's a way to like unwrap it and find a smaller version of the same problem, but it's smaller. All right. So this is kind of an example of what we want. And like inside of that problem, we can solve that in terms of a smaller version of itself. In terms of a smaller version of itself. Until we get down to, there's eventually going to be a smallest version of the problem that we can immediately stop. And then we can start like putting the dolls back on each other and building up the answer based on that, right? So that, in a nutshell, that's going to be what recursion is about, okay? And recursion is a way to solve, there's plenty of memes about it. There's a way to solve a bunch of problems, including this. This is a game called the Tower of Hanoi. Have you ever heard of that? It's a game where like you can only move one peg at one stack at a time, like this thing, and you can only put smaller ones on top of bigger ones. So you can't like do that, and then this one's bigger, this one can't go on top of that one. Like the goal is to move this stack all the way over to here, where you use this one as like an intermediate stage. So that's kind of the game, if you've never heard of it. It's the Tower of Hanoi. And recursion is a way to solve this problem and tell you exactly what moves to make. And you can't do it without recursion. So yeah, that's worth learning. So let's talk about it. So, all right, you're solving a problem in terms of smaller versions, that's key, of the same problem. All right, so yeah, the answer is no. It's not just circular reasoning. As long as things get smaller. As long as the problem gets smaller, you're good. So like, here's your big problem. Whee! Here's your big problem. What you want to do, I guess here. Here's your big problem. You find a smaller version of that problem inside of itself. It looks similar, right? Then you solve that one. And then you use that answer to solve the original version of your problem. You fill it in after that. So that's essentially what we're going to do, right? So you solve a problem in terms of smaller versions of itself, right? And so your goal with recursion, I'll give you a good example in one slide. It's, all right, you find... or I tell you, or you figure out that the problem has itself inside of itself. You find a problem with the same problem inside of itself in a smaller form, and that smaller problem we call the sub-problem. That makes sense to call it that, right? And then somehow we use that answer. Like we're able to get at that answer. We use it to build the final answer for the original biggest problem, right? And that's what we want. So yeah, that seems probably very vague and weird. Let me give you a good example of it now. So I claim that factorial, solving for the factorial of a number, that is a recursive problem, right? So think about it. That's me saying that, all right, somewhere within 5 factorial is another factorial, all right? So here's 5 factorial. 3 equals 5 times 4 times 3 times 2 times 1. Do you guys see a smaller factorial inside of 5 factorial? We can do this one together as a group. So remember that factorial is just like multiplying a bunch of numbers down to 1. Does anybody see a smaller factorial inside of 5 factorial? Yeah, you see 4 factorial? Does everybody see it? There's 4 factorial. It's chilling right there. Does anybody see any other factorials? There's not just 4, is there? Yeah, I see 3, 2. They're all there. There's 4 factorial. Do you see what I mean by the problems within itself now? There's 4 factorial. There's 3 factorial. It's weird. We didn't notice that before, maybe. I don't know. There's 2 factorial. There's 1 factorial. It's all there, right? 1 factorial. So they're all there. Usually when you're solving a problem recursively, though, you want to just find the next smaller one. So it was good to notice the 4 factorial. We want to find the biggest smaller problem. So that's where we go. And that's a little odd, all right? How can we use that to solve our original problem is now the question. Like, okay, that's recursive. We figured that out. We found like a smaller factorial inside of 5 factorial. We noticed that it was, all right, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. That's 4 factorial right there. And this is a pattern, right? We notice that, all right, another way to write this then is 5 factorial equals 5 times 4 factorial. That's still correct, okay? And this is a smaller factorial problem, a smaller. And we can use it to build up the bigger answer, right? This is a smaller factorial finding problem. Interesting. And this generalizes too. Like you ask for 7 factorial. Do you see like that's 7 times 6 times 5 times 4 times 3 times 2 times 1. In the same vein, 7 factorial is equal to 7 times 6 factorial. It's always in there, at least usually, right? So there's 6 factorial. Boop, just like that. So, okay, in general then, if somebody asks for n factorial, can you follow this pattern? Like 7 factorial is 7 times 6 factorial. 5 factorial is equal to 5 times 4 factorial. In general, n factorial is equal to n times n minus 1 factorial. Does that make sense, the jump that I just made there? That's the key. All right. Let me just rewrite it without the underlines. N factorial is equal to n times n minus 1 factorial. Interesting to notice that, all right? So that's us generalizing these kinds of cases, all right? And that's going to work usually. And we call that the recursive case, all right? There's going to be a couple ways to solve this problem. This is called the recursive case. This is the one where like we're unstacking the dolls, kind of. And that's called the recursive case. All right. And then there's still something else we need, because eventually this kind of formula, it will work for most numbers, but eventually it will stop working. All right. So we need to now find the smallest dull. That's our final task. All right. Because then we can get down to it and work our way back up. So, all right, we did it. We did the recursive case. That's how we're using the smaller factorial answer to build the bigger factorial, which is with an extra multiplication. If you think about it, working your way from right to left in that equation. And then we also need a stopping condition, right? Because this game is not going to last all day long. Watch. 5 factorial. If we follow our rules, that's equal to, all right, 5 is in 5 times 4 factorial. That checks out. That is correct. 5 times 4 is factorial, right? And then, all right, what's 4 factorial? According to our rule, again, we can use it. That's equal to 4 times 3 factorial, right? That still makes sense. Nothing's wrong yet. But what we're going to look for is a stopping condition, or smallest dull, right? It's when do we know the answer without having to do anything smaller? We don't have to ever calculate the smaller factorial. But for this one, this is still a correct thing. The math still checks out. Let's keep on trucking. All right, 3 factorial. According to our recursive case rule, we can unwind it, and that's equal to 3 times 2 factorial. This still makes sense, right? That's still correct in math. All right, 2 factorial, that's equal to, according to our rule, equal to 2. That's equal to 2 times 1 factorial. That still checks out, right? But maybe we want to stop now. You see it? All right, 1 factorial, according to our rule, if we want to keep doing it, right? That's equal to 1 times 0 factorial. That's starting to look a little weird, right? 0 factorial does technically exist. It is defined in math to be 1. So we could keep going, sure. And then according to our rule, 0 factorial would be equal to 0 times negative 1 factorial. And now for sure the universe has stopped making sense. There is, first of all, if you multiply by 0, you're multiplying your whole answer, right, by 0 eventually, that would make the whole answer 0. That would ruin it all, first of all. And then also negative 1 factorial, there's no such thing as a negative factorial. So we need to stop unwinding by the time we get to here. Does that make sense? We could just hard code. If you ever see 0 factorial, the answer is 1 or something. Or, probably because we haven't seen 0 factorial before, let's just cut it off right here. If anybody ever asks me for 1 factorial, that's the smallest dull. I don't need to go into 0 factorial. I don't need to do this unwinding anymore. The answer is 1. Just give that back to whoever asked. Does that make sense? Those are your 2 rules. And together they will solve any factorial. All right? That's called a base case. If anybody ever asks you for 1 factorial, I don't need to play this game. It's all right, the answer is 1. Call it a day. So that's how you do it. These are the 2 cases you need for a recursive solution. You need a recursive case and at least 1 base case. Sometimes the problem at hand, there are multiple base cases. But this one is we just need 1. You could have also done 0 factorial. That would have been technically slightly more general, but I think this was a good one. It's all right, if in general, this is how you solve a factorial in terms of a smaller one, but if you ever get down to just 1 factorial, you're done. Don't try the other rule. Just immediately just give back 1. All right? And now let's use these 2 rules to solve a factorial. All right, let's see how they work together. It's another way to think about it. Let's watch them unwind, get to the smallest dull, and then start wrapping it back up. Here. So here's how we do it. I think I'll make a new blank slide just to draw that. Let's copy in our rules there. There we go. And then, let's say somebody asks you for 5 factorial. This is eventually going to turn into a program. We want to write a program that does this. So this is where I'm going with this, because I know you know how to calculate 5 factorial in the other way. But this is how you could generalize it and write a program to solve for this. So 5 factorial, if we want to solve it recursively, we're going to do it this way. It's all right, are we either in the recursive case or the base case right now? We are in the recursive case because 5 is not 1, right? So all right, we're going to run this rule. To expand this, we're going to run this rule. 5 factorial is equal to 5 times 4 factorial. All right? That's what we want. That's equal to 5 times 4 factorial. And then, well, we know what 5 is. We know how to multiply, but we don't know what 4 factorial is because it's our job to calculate these things right now. We're the one that does the factorial. So all right, 4 factorial. Let's figure out what that is as a number. It's either we're going to solve for it using the recursive case or the base case. It's only the recursive case that applies here, right? So it's not 1 yet. So all right, according to our rule, 4 factorial is equal to 4 times 3 factorial. We're unwrapping it using smaller factorials. I'm like, all right, now if I just calculate this, give that back to 5 factorial, like we'll have an answer. It's like, all right, now our job is to calculate 3 factorial. So how do we do that? Again, it's not 1, so it's the recursive case. So 3 factorial unwinds into 3 times 2 factorial. And then we just keep playing this game, right, until we hit the base case. So all right, 2 factorial, you got to use the recursive case again, becomes 2 times 1 factorial. 1, draw a prettier 1 factorial. And then finally, to get this answer, we need to multiply 2 by 1 factorial, whatever that is. It's our job to compute it. Then we look to these rules, like, all right, I can either run this rule or this rule. You want to use the base case when you can. So like we're asking for 1 factorial finally. We've hit the base case, and so like we just give back 1 as our final answer. And now we have numbers for everything, right? So now like we're down here at the lowest point. We've worked our way down. Now we want to work our way back up. And then we'll get our final answer, all right? So like, all right, we now know the answer for 1 factorial. Here it is. So 1 factorial, that is 1. We're going to give back the 1 to whoever asked for it. Give that back. And so now the 2 factorial was waiting on 1 factorial. It knows that the answer was 1. It got that back from the base case, kind of. And now it can multiply the 2 by the 1. And that's its 2 factorial. That's 2, and it gives that back as its answer. See how that's going to, like, it's putting the dolls back on each other, kind of? That's what's happening here. And so now 2 factorial, we were waiting on that. We got the final number answer for 2 factorial. It's just 2. So now 3 factorial can do the rest, like multiply its 3 by the 2 that it sees here to compute 6. Give that back as 3 factorial. And that is correct for 3 factorial, right? That's how you can build up the answer again. So now 3 factorial, we know that's 6. We'll multiply 4 by that to compute 24. Boop. So 24 as 4 factorial. And then 5 factorial is waiting so long on 4 factorial. It just got the answer back as a number. It can finally do the multiplication by 5 to give back its final answer, build its final answer based on the smaller answer, right? The smaller factorial, which is apparently 120 for 5 factorial. 120. And that's how you can solve a problem that is recursive using recursion. You break it down, you unwind, unwrap, you find the smallest answer, and then you start wrapping back up with the answers that you received from the people below you. Does that make a little bit of sense? Because that's going to turn into a program, all right? Because I know you could make a loop that does a factorial. This is another way to write a program that like works in this way to do a factorial, all right? It's a new way of thinking, all right? And some problems, like for example, this one, can only be solved with recursion. You have to learn it. There's no other way. You can't use a loop to solve this or something. So, yeah, it's worth learning, I promise. So what we're going to do is usually, like when you write like you're trying to solve a problem, right? Usually you end up writing a function to do that, like factorial. Like you want to make a factorial of functions. You give me a number, I'll give you the factorial of that number, kind of. So usually in coding, that's what we do. So let's write a function that is recursive, that computes the factorial, all right? So what does that mean? Like somebody's going to call us, like I want 5 factorial. We'll call it like, I don't know, fact or something will be the name of it. Somebody will ask for fact of 5, like that represents they want 5 factorial. What it means to be recursive, what it means to implement in this way is that, all right, somebody asked for 5 factorial, we're going to ask for 4 factorial inside of 5 factorial, which if this is a function, that means we're going to call ourselves, all right? That's a weird idea. So fact of 5 is going to call fact of 4. And fact of 4 is going to call fact of 3. It's going to be weird, all right? A recursive function is one that calls itself, right? Because like it's our job to solve the problem, and so we're going to hand it off to ourselves in a smaller form now. It's defined in terms of ourselves, all right? So here, let's take our rules and somehow write code, all right, that corresponds to them. So here's what it's going to look like. It's like, all right, we're going to make a function called fact, def fact, takes a number n that we want the factorial of, and the job of this, right, is to compute n factorial, right? And so here's what the body of this function is going to look like. It's going to look really weird, all right? So let's think about how we did this on paper. It's like, all right, when we're trying to solve a problem recursively, we need to like figure out like, am I in the base case right now? If so, use it. Or am I in the recursive case? Otherwise, we got to use that one. So that's an if-else, isn't it? That just becomes an if-else in code. Like either we're in the recursive case or the base case, figure out which one, and go down that path, right? So if we were asked to compute 1 factorial, if we're in the base case, that means the n that we wanted to compute the factorial of was 1. So if n was exactly 1, n equals 1, right? Then we're in the base case. Somebody asked me for fact of 1, yeah? That's the base case. And what we'll do is we will return back, because it's our job to return, give back the answer, right? Return 1, because that's what the factorial of 1 is. It's just 1. Return 1, so that would work. And then otherwise, else, if we're not in the base case, if it wasn't 1, then we must be in this recursive case, yeah? So otherwise, we're in the recursive case. Recursive case. And then, now the question is like, all right, we're going to call ourselves, because it's our job to compute the factorial, right? In the recursive case, we want to take our n and multiply it by the answer for the one smaller factorial. We don't know that answer, and it's our job to compute it. Like, we're the ones computing factorial, so what we do is we hand it off to ourselves. We hand off this calculation to a smaller version of ourselves. It's like, all right, let's save it away for a second. Like, x equals fact of n minus 1. So we just call ourselves. We let a smaller version of ourselves handle the problem. This is called the recursive call. When you make a function, you're calling yourself. It's a recursive problem. It's called the recursive call. That's what we do right there. We're going to use that now. We're going to use the recursive call to compute our final answer. It's like, how do we build up our final answer? Say we got something back for x. This is x now. We just need to multiply our n by that thing, and that's our final answer. That's how we build up the bigger answer from the smaller answer. Just assume we got it back. Due to the magic of recursion, I'll draw a picture for you to prove why it works. It will just work, and we want to return our n times that smaller problem's answer, so x. Okay? So that's what the code looks like, and somehow it's gonna do this, all right? It's going to loop, right? Because you think about it, like you're multiplying a bunch of numbers down to 1. It's kind of like a loop. There's no loop, there's no while, there's no for anywhere here. It's gonna loop without looping. It's crazy. So here, let me code that up to you in idle. And I'll give you this code this time, and we'll watch it work. And I'll try to draw a picture to prove to you why it's working. It's gonna look similar to this one. But it's like all those functions, like there's going to be a bunch of calls to the same function all existing at once, and then it's going to start unwinding, right? That's what's going to happen. So I would like to make a new program in today's folder. So this is lecture 29. And I'll call this fact for factorial, but I got to put it in the right spot. '29. All right, so let's do exactly what we did here. We want def fact of n. We want the factorial of some number n. And so this is a function that computes n factorial. And so, all right, here we are. And we're either in the base case or the recursive case, if else, right? Because we're solving, it's really this, right, that we're implementing. If n is equal to 1, somebody asked me for the factorial of 1. That's the base case. Return 1, because that's the factorial of 1 is just 1. Otherwise, and we're in the recursive case. So we need to give back our n times n minus 1 factorial. But it's our job to compute n minus 1 factorial, so we hand it off to ourselves. Like, all right, call fact of n minus 1, call 4 factorial or whatever it is, and we can save that away, right? This will eventually, because we keep calling on smaller things, it will eventually make its way in a roundabout way down to the base case and start building the answer up. Eventually, we will have an answer here. You just get to assume you get the right answer mathematically for n minus 1 factorial, and then you can return your final answer in terms of that, n times that x, right? That's it. That's how you implement it, and boop, if you print the fact of 5, it really will become that 120. It really will do the right thing, even though it looks a little confusing. Somehow, we got 120, all right? Are there any questions right now about what happened? We'll draw some pictures. I know this is a little weird looking, but here, let me print. Like, fact is going to be called a few times. Like, we're calling ourselves. Factor 5, I claim is going to call factor 4. You can imagine factor 4 is going to call factor 3. Let me show that to you. So if I print at the start, like just as we get called, print like inside fact of whatever we are right now. So I can put here the string version of that m. This is like print fact of 5. Like it'll make a big string that tells us where we are right now. So like it'll print inside fact of 5 for the first call, inside fact of 4, whatever n is. It'll print it out like that we're inside that call. And look, initially we're inside fact of 5. It called fact of 4. We're inside fact of 4. Fact of 4 called fact of 3, 2. We got all the way down to 1. So those were all function calls. We called fact 5 times secretly. I guess 4 times secretly. 1 time explicitly. All right? Is that making a little bit more sense? It's a little odd. All right? So it's just always going to work like that. And like same with like fact of any other number. Print fact of 3 is going to call fact of 2, which we'll call fact of 1. And somehow we'll get down to the base case, unwind, and start building the answer back up. Because now it finally has something for that x. Multiply your 1, your 2, your 3 back into it. It will eventually work out. Okay? So that is the secret. That's what's going to happen. And yeah, here, I'll comment this back out. Highly encourage you to play around with printing. It will help you figure out what's happening here. Also, try shoving this into the Python tutor website. I'm going to draw you a picture that's going to be similar to that. But like, that also is very helpful to see what's going on here. That Python tutor website that draws what's happening. But I think I would like to draw for you what's called a stack diagram. I showed you this like briefly once, but it's a stack diagram. Remember, it's just like a stack of like work to be done functions that are being called. Right? What exists where? So it's just going to be like a stack of papers. It's a stack of work to be done. Like the person who's acting right now is always going to be the thing on the top of this stack, and the person right underneath us is always going to be the person who wants our answer, right? Stack of work to be done slash, it's going to show who wants whose answer. All right, so here's what's going on. So at the very bottom level, before I called this like the outermost code or something, but let's just say like we're in the outermost code and we're calling print fact 5. That's our job, right? So we just called print fact 5. So that's like some stack of work to be done. Print fact 5, okay? It's like really it's just the print call. We're calling print right now on something. And print is like, all right, I'm going to print this thing for you. Whatever fact of 5 is, it does not know what fact of 5 is, so print's going to call fact of 5. I hope you see that. So that's some new work to be done, and we add it to our stack of work. All right? So print fact of 5 will call fact of 5 to figure out what in the world is fact of 5 so I can print that. Give me a number back, please. All right? So that's new work to be done. So it's like print is going to wait on fact of 5. Fact of 5 will give its answer right back to print. Does that kind of make sense? That's how you read a stack diagram. And so, all right, fact of 5, it's a function call. Every function has its own little variables that are local to it. It's like this 5, I was a little lazy, but really 5 is n, right? So we call fact of 5, so that means n is 5. And we're in this code. And so, all right, is n equal to 1? No, 5 is not 1. So what's the code going to do? It's not going to return 1. It's going to go to the recursive case. It's going to be like, all right, I'm going to make a variable called x. And inside of that, I will put the answer to fact of 4, right? Because my n is 5, n minus 1 is 4. I need fact of 4, and I want to put it right there, all right? And so we don't have an answer to put in x yet. Fact of 5 needs to go off and call fact of 4. We need a number here. So fact of 5 will call fact of 4, and it's going to wait on this line to get it back. Does that make sense? It is not ready to return its answer. It's not ready to continue. It's going to be stuck on this line until it gets its answer back. That's what's happening. And so it's essentially Python doing this, all right? Essentially Python doing that. So here, fact of 5 is going to call fact of 4. And what that means, right, it's going to be called with another n, right? N is 4 in this case. So fact of 4 and 5 are running at once right now. Fact of 4 is the one in charge. Fact of 4 is what we're in right now. That is what has control, because fact of 5 is waiting on this line. Yeah? And now fact of 4, with its n being 4, is going to try to run and figure out what its answer is. So, okay, and it knows to give its answer back to factor 5 when it's done. That's the person underneath it on the stack. So, okay, we're in factor 4 now, n is 4, still not 1. So we're in the recursive case, and so this one's going to make its own x variable, right? It's a separate one. It's part of its function call. And inside of that, it's going to shove the answer to fact of 3, because n minus 1 for fact of 4, right, is 3. But it does not have fact of 3 ready. So again, it needs to stop. It's going to pause on this line and wait for the answer. It needs to go off. Fact of 4 must go off and call fact of 3 so it has an answer to put into x. And then it knows how to multiply that, right? It needs a real number, though, and it needs that to be computed first. So fact of 4 is going to call fact of 3. All right? So now there's 3 calls to fact waiting right now. I guess 2 calls waiting, one in action. Fact of 3 with its n holding 3, right? They're all separate calls. They're all running at once, right? But the ones underneath are paused right there. So now we're in factor 3 at the start, right? Does that make sense, what's happening right now? Because like that's key to understanding. Please yell at me if you have any questions about that. 5 is called 4. It's called 3. And we're going to get all the way down to 1. That's what's going to happen, right? So factor 3, again, n is not 1. So it's going to make its own little x variable that holds the answer for fact of 2 because it needs that, right? It will multiply its fact of 2 by its 3, give that back. It does not know what fact of 2 is. It needs to go off and compute it. That's a function call, right? It needs to go off, ask the function, which happens to be itself, I guess, in a smaller form for that answer. All right, so fact of 3 is going to call fact of 2. Fact of 2 is going to be the star of the show now for a second. Fact of 2. With its n holding 2, right? It's another separate call. It has its own n value. It's a different thing that was called with, right? And again, like fact of 3, 4, and 5, they're all waiting on the person above them. Yeah? They're all waiting on this line because they don't have an answer for their smaller factorial yet. We're still trying to compute that, all right? We're getting all the way down to the base case. So, all right, we're in factor 2. N is 2, still not 1. We're in the recursive case. So, all right, it's going to make its own x variable. That's going to hold the answer for fact of 1, whatever that is. It does not know the answer. It needs to go call fact of 1, right? Fact of 2 needs to call fact of 1, get something to put into x. Nobody's filled in their x variable yet. They just know that it needs to exist eventually. So they're all paused right here for one last round. Fact of 2 has to wait on fact of 1, and then it's all going to start unwinding. The fact of 2, all right, I know my answer. It's my 2 times fact of 1. I need fact of 1, please. So fact of 2 will call fact of 1, and so now there are 5 calls to fact on the stack. All right, on the stack of work to be done. N is finally 1, just 1, and that's our base case. So everybody, fact of 2, 3, 4, and 5, they're all waiting on this line for the smaller factorial above them. We don't know the answer yet, but now we're going to eventually get at those answers. All right, everybody's waiting. Like fact of 2 is waiting on fact of 1, fact of 3 is waiting on fact of 2, 4 is waiting on 3, 5 is waiting on 4. They're all waiting on the person above them, and now it's going to finally like kick off because we're in the base case. We finally have a concrete answer once and for all. All right, so fact of 1, when n is 1, it's like, all right, oh, cool, we're in this one. So that's the base case. We return 1 back to whoever called us. The answer for fact of 1 is 1. It returns that to whoever called it, which was the person underneath it on the stack. And that is this. So fact of 1 returns 1 back to whoever was asking for that answer. And I guess I've run out of room. Let me move this over. So there, fact of 1 is returned 1 back to fact of 2. That's what just happened. And now fact of 1 is done working. Once you return, you're done with your function. Everything that was u goes away. Really, I should be erasing this, but I'll just keep it here so you can see it later. So we did it. Now fact of 2, who was waiting right here, finally got an answer. It sees 1 from the fact of 1 call. Right? It got back 1. It can put it in its x finally, there. And now it can finally continue. Now it's unwinding. See it? So now it can return its x, which is n, or sorry, its n, sorry, which is 2, times 1, which it got and put in x finally for the factorial of 1. It's waiting so patiently. 1 times 2 is 2. It returns that to whoever called it. So fact of 2 is fact of 3 who is waiting. It just now sees fact of 2. My answer is 2. That's what it's saying. And now fact of 2 is like, I'm done. Back to you, fact of 3. So really, these are all deleted. You can think about it, erased. And fact of 3 is on top again. They're in charge. So fact of 3, patiently waiting right here on fact of 2, it finally got an answer back. got the 2 back. Do you see how it's essentially the code equivalent of this? That's all happening now. All right. So it got the 2 back. It can shove that into x. And its answer is its own n times x. The 3 times the smaller factorial, which we have a concrete answer for now, which was 2. That is going to be 6, right? And that's what it will return back to whoever called it. Returns the 6. And that is the correct factorial of 3. Yeah, now it's done. And now we're in factor 4. Who is waiting on factor 3? Right here. They're all waiting on this line, right? In their own version of the function call. So now, all right, factor 4 is waiting on factor 3. It got the answer of 6 back. It can place that into its x variable. It has something concrete now to use. And its final answer is in terms of that, right? It's its own n, which is 4, times the factorial of 3, which we now have the answer of 6 for. 4 times 6 is what it returns back to whoever called it, which is 24. And that is the correct factorial of 4. Do you see how it's working its way back down? It's using the recursive case rule. It really is doing just this, just in code form, using the stack, right, of function calls. And now finally, we made it. Factor 5 is the thing on top. Everything else is erased, you can imagine. Factor 5 was waiting ever so patiently on this line right here, right, on factor 4. It took forever, but now it's there. It's got the answer for factor 4. It sees the 24. It sees a real number. It can place that into its x variable, 24. And that now it's off to the races, because then it can continue. Now I know, all right, it knows how to multiply 2 numbers together finally. Now it has a separate number for the answer. So now it can multiply its n, 5, times the 4 factorial, which it placed in x, which was 24. We finally have that. And it can return that final answer, that multiplication, to whoever called it. That's 120. Back down to print, and print's like, all right, I was waiting for factor 5. I have 120. I see that the answer is 120. I know how to print an int now that I have one, finally. And then you see 120 on the screen. All right? And then I guess factor 5 returned back to print. That's how it worked. Does that make sense? Does that help at all? Are there any questions about that? Because that's what's happening. Factor 5 is calling factor 4, is calling factor 3, factor 2, factor... They're all existing at once for a split second, and then they all start unwinding. Factor 1's done, factor 2's done. It starts giving back answers. Okay? So it's making its way down to the base case and building the answer back up, starting from the base case's concrete answer. Because that's the only time you have a concrete answer, right? And then once you start using that, you can use the recursive case rule to make the next bigger answer, the next bigger answer, the next bigger answer. That's what's happening. Okay? And that's the magic of recursion. All right? I do believe that's as fancy as I want to do. So, yeah, I think that's most of what I want to say. There is something magical kind of going on that you'll have to wait until a later computer science class if you're interested to learn about. It's just like, it's not immediately obvious that like when you call yourself, right, that it's really going to give back the mathematical smaller factorial answers. Like you're calling yourself, it seems circular in a sense, but you don't have to think about it making its way down or anything. You don't have to think about any of this. You can just kind of be lazy. And for a weird reason, which I can't really get into in this class, you just get to assume that this call right here, it really does give you back n-1 factorial. Just use it with that in mind. Pretend it does, and it really will give you back n-1 factorial, the real mathematical answer, as long as you do everything else right. As long as you do, like, build up the answer correctly based on that, as long as you have a correct base case, this call really will result in n-1 factorial, the answer. You just get to assume that it does for an interesting reason. It has to do with what's called proof by induction, if you've heard of that, if you're a math major or something. So that, I guess that's the nitty-gritty detail for anyone who wants to look that up. But I think that's all that I want to talk about. Are there any questions about recursion, this idea of finding a problem inside of itself, defining it in that way, and then making a program that kind of loops without looping? You're going to call yourself usually. You make a function to solve for this thing. It's a very fun topic. It is a bit of a difficult topic, though. So if you understood any of that, pat yourself on the back. And I think with that, that's all that I want to say. There's no new assignments. You have every assignment in the class out right now. It would be evil to start giving you more because like the last week of classes is here. And then we just have the final. So next week it's going to be nothing but final review. And remember that all late assignments are due on next Friday, not the finals week Friday, but next Friday. So if you want to turn something in late, keep that in mind. I'll talk about that more later. But yeah, I think that's all that I have for the day.